Welcome back to a new exercise. We're going to continue the study of accelerated motion. A plane moving 110 meters per second touches the runway of a small airport and applies the brakes so that the magnitude of the acceleration is 10 meters per second squared. How long does it take to stop? Find the minimum length of the runway for a safe landing. Let's start by looking at the quantities that are given to us in the problem. We have the speed of the plane. So this is the initial velocity. We also have the magnitude of the acceleration. Those are the two quantities. These are the only two numbers that we have for solving this problem. So as usual, in my personal recipe, the next step after you identify all the relevant quantities that are given is to draw a cartoon. And for the cartoon, the first thing we do is we select our coordinates. So we start by drawing a line and call this our x-axis. As usual, we make it from left to right. Somewhere here we set the origin. So this is x equals 0. And this will be, we're going to select this to be the point where the plane will touch down or will touch the ground of the airport. Okay, so we have our plane here, something like this. Suppose this is a plane and it's coming down and it will touch the ground right there. This point is what we call x equals 0. And as soon as it touches the ground, it will apply the brakes and will start slowing down. So I will try to draw my plane here. So this is the plane, now with the wheels down, and this plane will be moving to the right, but it is slowing down. And at some point, at some distance that we can call d, the plane will come to a complete stop. In other words, the velocity here is 0 at this point. And that is very important, because we are being told that the plane will come to stop. Stop means that the velocity is equal to 0. Now that we have our cartoon, we can apply the equations. We can write equations for our plane. As we know, for the case of accelerated motion, we have 3 formulas. 2 of them involve time, 1 of them does not involve time. Since we are being asked about how long does it take, this means time. So we have to use one of the formulas that involves time. We have a formula that says that v, that is the velocity at any given time, will be given by the initial velocity plus acceleration times the time. So this formula involves time, which is what the quantity we're interested in, involves the acceleration that we have, involves the initial velocity that we also have, and on the left hand side we have the final velocity, which we also know because we want this to come to a complete stop. So this is exactly the formula we need. This is the way we can decide which formula is good for a given problem. Okay, so let's set at the point where the plane comes to a complete stop, we set the velocity to be 0. So this becomes v0 plus a t. And we're interested in t. This is the quantity we want to find, so we need to solve for t. For this, we pass this v0 to the other side. So this becomes minus v0 equal to at. And now we pass the a to the other side. In other words, we divide in both sides by a. This becomes minus v0 divided by a is equal to t. Excellent. So we have the time in terms of quantities that we know. I will continue here on the other side. So I will write this expression again. T is minus v0 divided by a. We get minus v0 is 110 meters per second. Divided by the acceleration. Here we have to be very careful. The acceleration is a vector, just like the velocity that we considered at some point when things are pointing in different directions. So let's see what is the acceleration doing in this particular case. The acceleration is slowing down the motion. So the object is moving to the right, so the velocity is in that direction. but the acceleration points in the opposite direction. So if we could draw the acceleration, it would be an arrow pointing to the left. This is the acceleration. This 10 meters second square is the magnitude of the acceleration, is the number, but it doesn't tell us anything about the direction. We need to infer that from the problem. In this case, since the acceleration is slowing down the plane, this means that the acceleration points in the opposite direction of the velocity. The velocity is pointing to the right, so we call it a positive quantity, and the acceleration is pointing to the left. Therefore, the acceleration is a negative quantity. So when we write it here in the expression, we have to consider that extra sign. So this is minus 10 meters per second square. The two minus here will cancel, and we're going to end up with a positive quantity. In this case, 110 divided by 10 is just 11. And the units, we have meters per second divided by meters per second square. Therefore, there will be an extra second in the numerator. As expected, because we're finding here a quantity which is time. And there we have it. This is the answer for the first part. How long does it take to stop? 11 seconds. For the second part, we're being asked for the minimum length of the runway for a safe landing. That means we want to find this distance d. That is where we are being asked in this part. So this formula here does not involve distance. The other two formulas involve distance. So we can write this simply as, there are two ways we can do it. One way is to use the formula that only involves the velocity. So there is this v square equal to initial velocity square plus 2 times a times the distance, which in this case is d, so I will just call it d here. And we need to solve this formula for d. That means we take the v0 squared to the other side, to the left, and now we divide everything by 2d. So I will switch the sides to have more room. D can be written as v squared minus v0 squared, all divided by 2a. And now we plug in numbers. V squared is 0. 0 meters per second square. Because the final velocity is 0, we want this to come to stop. The initial velocity is 110 meters per second. Everything here is squared. And now we divide by 2 times the acceleration. And again, just as before, the acceleration has a minus in front. So this is 10 meters per second squared. We can plug this in our calculator. And we have 110 squared divided by 2 times 10. Notice that I did not include the minus signs because they will both cancel, the one in the numerator with the one in the denominator. So I simply ignore the minus sign. And this is 605. 605. And the units here will be meters. We can check that because second square will cancel with the second square, and meter squared divided by meter is meter. So here we have it. This is our distance. Notice that there is also this other formula that says that the distance. Notice also that there is this other formula, the ones that doesn't involve time. Notice also that there is this other formula for distance, which is initial position plus initial velocity times time plus 1/2 at squared. We could in principle also use this formula, where the initial position we know is 0. The initial velocity is 10 meters. The initial velocity is 110 meters per second. times the time that we found in the previous part to be 11 seconds, that is the time that it takes for the plane to stop, plus 1/2, which is 0.5, times the acceleration, which is minus 10 meters per second squared, times the time again is 11 seconds. And the time has to be taken square. So we could in principle use this formula. Let's see what we get. Back to the calculator, we have 110 times 11 seconds. That is, it's a big number, let's write this down. 1, 2, 10. And this will be in meters because meters per second times second is, of course, meters. For the second term, we have 0.5 times 10 times 11 to the power of 2. That is 605. Again, in meters. Notice that I put this minus here. This minus comes from this minus here. The minus from the acceleration. Now if we take this difference, this happens to be 605 meters. So we get exactly the same result as before. So it doesn't matter which formula we use, we're going to get the same result as expected. All the formulas have to work. In the next problem, I'm going to combine in a single exercise. Some part of the problem will involve acceleration, the other part will be uniform motion. So we have to remember all the formulas that we saw for accelerated motion and the ones that we saw at the beginning, trying to mix everything together, making it a little bit more complex, but we're going to see that it's not that hard. It's good practice. Don't miss that exercise.